Okay. Okay. So hello everyone. Today I will present you a paper called Communication Complexity of Common Voting Rules. This paper was written by Vincent Cazeirgues and Thomas Sandholm in 2005. And so I will explain what is communication complexity. So here you have a picture of a voting rule. So you have voters here and they have preferences. And the voting rule is this process. So it's this arrow here that elects a winner. But the problem of communication complexity is to know, here they have preferences, but how many information do you need in order to elect a winner? Like, what do you need to communicate to elect the winner, and how, depending on the voting rule that you use, how many bits of information do you need to give in order to obtain a winner? So for this to be done, you need to define something called a communication protocol. And so it's a bit different from a voting rule, because in the communication protocol, you determine how the relevant parts of the vote are actually elicited from the voters. So you just focus on communication. It's just a way to say you focus on the communication. So first, I will give an example to really show you the difference between what we call a voting rule and what we call a communication protocol. So for example, we are going to look at plurality with runoffs. So it's the French system. So for those who don't know what is the French system, you first go vote once and you give your favorite candidate. And then after the first vote, the two best candidates are kept, so the candidates that has the most votes, and then you go vote a second time to choose between those two. And so this is just here I just gave what is the voting rule, so what's the principle. And here is some communication protocol you could use. So just to see the differences, here, for example, I emphasized on add one vote for their top candidate, for the top candidate of a voter. And here I use the word ask. So ask them their top candidate. And this just is to focus on the communication. So to show that they are going to communicate their top candidate and that they are going to use a number of bits to communicate their top candidates. And so the communication complexity of a problem is the worst case number of bits sent in the best communication protocol for it. Okay, so you take the best communication protocol and you see in the worst case how many bits are going to be exchanged between the person that votes and some central authority that collects the vote. Okay, is it clear for everyone for the moment? Yes.
Just you put in parentheses, correct? Is it related to error in communication, which suppose that the communication is perfect? Or...
You suppose that the communication is perfect, yes.
So why only the communication? Also to compute something? Why not the processing complexity?
So this is just to focus on communication, and in this particular setting, you don't take into consideration the actions that the central authority may do to elect the winner. So it's just a focus on this particular thing. Okay, so just so that you are not lost in what follows, M will always designate the number of candidates and N the number of voters, and the communication complexity of the voting rules will be expressed in function of M and N. The set of candidates is sometimes denoted C, and for every voting rule except approval voting, that I will explain later, for every voting rule, we assume that the voter have strict preferences over the candidates so that they are able to provide a ranking. Okay, so here is the list of voting rules investigated in the paper. I just joined them by complexity. You will see at the end I'm a bit spoiling, but you will see at the end that all these rules have the same complexity, all these rooms have the same, and all these rules have the same. The ones that are in bold character, I will detail. So I will explain the voting rule, and then I will explain how we obtain the complexity. And those ones I will just show in the last table their complexity, but I will not talk about them. Okay, so let's start with those ones. So, oh yeah, so one thing to obtain the complexity, they do it by obtaining upper bounds and lower bounds, and they are tight except for one voting rule. We will see which one. And so to obtain an upper bound, there is a common upper bound to every voting rule except approval. Again, I will detail approval later. And so it says that the communication complexity of any rank-based voting rule is in big O of nm log m. So this thing, rank-based voting, is just that you are able to provide a ranking of the candidates. So that's why I assumed that voters have strict preferences in the voting rules. So to prove this result, the proof consists of designing a communication protocol that works. And so this gives an upper bound. So the communication protocol is as follows. Every voter sends their ranking to the central authority, and then the central authority sends back the name of the winner to all voters. And so in this, again, you don't take into account the actions that the central authority may do to elect the winner. You just consider the communication. So you just consider this thing and the sending back the voter. So what's the complexity of these 2 points? So the first step, when you give the position of one candidate, it requires log m bytes because you have like just m candidates. So to provide the position, you have between 1 and m positions. So you need log m bytes to give a number. And so as every voter gives a ranking, every voter, the complexity of them communicating their votes is m log m, because there is n candidates. And so you multiply by the number of voters n, and you obtain this for the step 1. The step 2, you usually ignore it because it's less than the first one, because it's just n log m bytes. You just communicate the winner to every voter. So overall, the complexity of this communication protocol is big O of nm log m. And this is an upper bound for every rank-based voting rule. Now, so this is an upper bound for all voting rules, but you will see later that some voting rules have a better upper bound, and always the proof consists in designing a communication protocol to prove upper bounds. And we will see some rules with some communication protocol that do better than this one. Yes?
Can you tell a bit more what communication complexity means in this case? I mean, is it just the representation of the information?
Yes.
Because I don't understand why this is an upper bound, because if any voter just needs to send its own ranking system, and you say you have a channel between any voter and the central authority, and every voter just needs m log m, because it only needs to send an ordered list of preferences.
Yes,
so
but
multiplying by n,
because you have n voters, so it's the communication complexity of the whole process. Yes.
The global with all the voters.
Yes, the global.
So yeah.
No, because I mean, if you consider n point to point, I mean, maybe it's through engineering this question, because if I have n cables,
yeah,
each cable is just m log m.
Yeah, but you mean cables.
You can normalize by n in the end if you want, but it's just a matter of definition.
Yeah. But I think they take into account the number of voters, because usually n is large, and so they want to make it appear in the complexity communication, because it can be large, and so Yeah.
But even conceptually, at the center point, you need to receive the n messages. So in terms of bits received by you, n times n of n.
Can't there be something like joint encoding or things like that? No, I mean, it's many to one, right?
Mhm.
So the channel in the channel series sense, right? It would be no. Okay, it's an upper bound.
Yeah, it's an upper bound, but even in this case, at the point where I don't, it depends how you define for me the number of bits that is involved. But at the end, each voter will have to send n log n. So at the entry point of the network, you will have.
Yes, but it's a joint. It could be seen as a joint encoding. Assume we are frank. You could say your order is just the opposite of mine. So say because you then in terms of ranking, right? So I mean, no, but it's the good answer is that it's just another problem.
Okay, so this is the method to obtain upper bounds, and there is also a method to obtain lower bounds, and this relies on something called pooling set. Okay. Is it okay? Can I? Okay. Yeah. Okay, so there here you have a general method to obtain lower bounds that relies on something called pooling set. So a pooling set is a set of vectors of ballots, so of votes. So you take one, so you rank the voters 1, 2, 3, and then every voter will give their vote, and this is a vector of ballots.
Every voter gives a rank.
Not necessarily. You will see later that it's a ballot, and depending on the voting rule, it's not necessarily a ranking. So you have a vector of votes, and so you take a set of such vectors, and they have to satisfy the two constraints here. So first, if you apply the voting rule to each vector, it gives the same winner, okay? But if you take a pair of vectors, you take a subset of votes in each of the vectors. They have to be of the same size as the previous vector. When you apply the voting rule to this subset, it doesn't give the same winner. This is a bit fuzzy for now, but I will show example, and I think it will be better with examples. But if you have questions, go on.
Can you explain again what is a vector of ballots for the union?
So you rank the voters from 1 to n. Okay, so you give them a position, and each voter will give their vote. And so the vector of ballots is just the votes of the electors, but in order.
It's a list.
It's a list, yes. It's a list of votes. You order them arbitrarily, but they just have to have the same position in every vector.
So to understand,
Yeah.
Position key corresponds to voter key.
Yeah, that's just saying that. Yeah. Okay. This is a bit fuzzy, but with the example, I think it will be more clear. Okay, so then you have a theorem that says if a voting rule exhibits a pooling set of size k, then its communication complexity is at least omega of log k. And this is the general method to obtain lower bounds. It will always be to exhibit a pooling set and of the right size, and then you will have the lower bound. This is not proven in this paper. This is proven in a previous paper called Communication Complexity. And I haven't read it. So if you have questions about why this is true, I don't know.
There are multiple pooling sets. It's the maximum bits.
Yes. Yeah.
The largest.
Yeah, yeah.
So for each pair of vectors, there is a subset of ballots in the union.
Yeah. So you take a vector,
Yeah.
two vector, you take the union, and then you want to either take, so the phrase is, the sentence is not really well written. So for the union, you either take the vote in the first one or in the second one for every voter. So for voter K, you either take the vote in the first vector or in the second vector.
Then it is another vector of
Yes, and then you have another vector of votes.
basis, in fact,
Yeah.
And for these vectors of ballots, is it assumed that they are of size n?
Yes,
Okay,
it's
so
assumed
it's
that they
two
are size.
profiles in
Yes, it's
Okay.
yeah.
Two different profiles, and when you pick
Yeah.
a preference from one profile or the other for each voter,
Yes.
then you have a different
This
result.
means
Yes,
that
exactly.
You may have a
you count all the possible outcomes. I don't know. I
But
don't know.
there will be an example, you said.
Yeah, there will be an example.
Perhaps it will help to understand.
Yeah. But it's just that here the order of the voters is important because, for example, if you have two voters, one voter vote for the first vote for one and the second vote for two, it's not the same as one vote for two and two vote for one. So that's why the order is important.
Maybe another way to say it for communication and network-oriented people is to say that voters have identifiers, and a vector of ballots is simply to give the ballot of each voter of each identifier. And when you take a subset of ballots in the union, mean in fact that for each identifier you choose either a ballot from the first vector or from the second vector.
Yeah.
That's it?
Yeah, that's it. It's just that actually this sentence I wrote is not correct. Yeah, it's just not correct.
The profile,
it's
keeping the
yeah.
identifiers.
Yeah.
And so, just again, now I look at the theorem, right? So there was this issue we were discussing about the complexity. So here, you in the earlier discussion, you were assuming that, for instance, there was no way to do joint encoding or something like that. This were independent. So what are the assumptions of this theorem actually? So if you think in terms of well, it's many to one, so it's you have many transmissions of data which have to arrive to a given and so you count the number of bits, but the way to encode. So you assume for this theorem you assume that there is no joint encoding, right?
Yes.
The bits sent are just the
Yes.
I don't think so.
No?
I don't think so. I don't think that you do such an assumption. No.
Okay.
Essentially, what you do in the end is that you show that you need to distinguish elements from a set of certain size.
Okay.
So if you do this, whatever the encoding, anyway, in the end, you will have a certain communication complexity.
Of the
Yeah. So anyway you do it, if you need to distinguish several cases and be able to distinguish this case, you will need to there is a certain quantity of information that you.
Maybe you have an example of that?
Yes.
Okay, thanks. Just thanks.
Okay, so first, let's go back to the upper bound for plurality. So the algorithm I previously shown, here is the communication protocol I previously shown. And here is the communication protocol for plurality. So let's look at it in detail. So first, plurality is just you go vote, you tell your favorite candidates, and then the candidate that wins is the candidate that has the most votes. Sorry. So for each voter, you ask them their top candidates. That's it. Then the operations you do to count who is the winner, they don't count again, because we are just looking at the communication complexity. And then you just transmit the result of the election. And so for plurality with runoff, it's the same thing, but you do it twice. And so first you ask the people their top candidate, then you keep the two best candidates, and then you ask them their favorite candidate among the two remaining, and that's it. So here it's just enough to look at the communication complexity here, because here is just twice this one, so it's the same here. So when you ask them their temp candidates, it just requires log m bytes, because they just need to give you the name of the top candidate. And so because you do it n times, so for the n voters, the total complexity of the algorithm is n log m. And so that's it. And for this, it's the same. And so you see that here, the upper bound is better than the general bound. And it's because here, you don't need the whole ranking to do the process. You just need to have the top candidates. Okay, so is it okay for everyone? Okay, so for the lower bound now. So the lower bound is also n log m. And to do so, we are going to construct a fooling set. So the fooling set is as follow. So you take n prime, which is n minus 1 divided by 2. And so for every voter k, for every k, voter 2k minus 1 and 2k vote the same. So for example, voter 1 and 2 will vote, for example, for candidate A. Okay, and you do this until n minus 1. And you just say that the last voter votes for candidate A. Okay, so you have a sequence of votes with every time the neighbors vote the same, okay, 2 by 2, and the last one vote for A. And you also assume that every candidate receives equally many votes from the first to n primes voters. So you have a condition here on n. N must be odd, okay, because otherwise you cannot divide it by 2. And I will explain later what this implies on actually this bound. But for the moment, let's assume n is odd, and let's construct the fooling set here. So now we need to ensure that this is a fooling set. So first, when you take every ranking, when you take every vector of votes, you actually see that it's candidate A that wins every time, okay? Because every candidate has the same number of votes except for the last one. Yes.
Sorry, I probably missed something. So we have any number of candidates M, or just two
No, there
candidates?
will be a condition on M also.
Okay, because here it seems to assume that M divides.
Yes, there is actually a condition on M.
Okay.
Yeah, there is a condition on M and M.
And if it's
Okay,
not
so
the case, you
maybe
see that it's
I
not
will
that
discuss.
different, but,
Maybe I can discuss it now. It's just that you have, in fact, a condition on N and M. N must be odd and M must be divided by N, or the contrary. Anyway. And actually, so this ensures that these fooling sets exist for infinitely many N and M. And this bound is actually what they call a non-deterministic bound, because it's true for an infinite number of N and M, but not for all. So that's just like a thing that they did in the paper, but okay. But they say that it's not a problem. They don't explain what is not an issue, but they say it's not an issue. So yeah.
Sorry, but maybe it's a very stupid question, so I apologize for the stupidity. But a lower bound, I mean, in my interpretation, it's like the best case scenario for communication complexity, right? So it is what happens when everything goes as planned.
Yes.
And I mean, in this case, is every voters vote for the same person, right?
Yes.
So the real lower bound is when everybody agrees immediately on the first shot on who is the.
So here we are looking for plurality. And even if they vote the same, they still need to vote and give the name. And so it's quite normal that you will have at the end n log m, because when you think of it intuitively, you kind of understand that, yeah, every voter still needs log m bytes to do.
Yeah, sure.
So
I think that the misunderstanding is different. In fact, it's on what is the best case scenario. In fact, the lower bound is the worst case, the worst case of the best protocol.
Okay.
It's not what happens on the best instance of the problem.
Okay.
It's what happens with the best protocol.
Okay. Yeah.
Okay.
So what you consider here is a case that may happen, and then in that case you prove that is the best protocol. You must have at least.
Okay, so is everyone convinced that every A when we apply plurality? Okay, and so now you need to find two vectors. If you take, if you mix them, it's not going to give A. So because these are vectors, there exists an index K where they disagree on the candidates. So where 2K minus 1 and 2K will disagree in both vectors. They will, like, for example, we can think of one vector where they vote A and the second where they vote a candidate B. Okay, so the new vector consists in taking every vote from the first vector, except for this index K, where you take the vote of the second vector. So instead of A, you just will put B. And in this vector, B will win because it will have one more vote than A. So you have a pair where if you mix, you indeed end up with another candidate winning with plurality. Okay.
One pair.
Yes. Yeah. No. It's for every pair. Let me look. I'm not sure. I think it's one pair because every pair you cannot necessarily do it.
It's just one pair.
It's just one pair. Yeah, because you cannot necessarily do it for every pair, I think. Okay, so this set is of size this. I will not prove it, but as you can see here, you kind of see the dependence between N and M, and that one needs to divide the other. And also, this is a result of the paper. I will not detail it. This is the result of the paper. So this is greater than this thing, which is omega of n log m. And so that's how you have this bound in the end.
It's not clear here for me is why the Falling set size produce a lower bound.
I don't know.
No,
Because yeah.
There is no easy intuition.
I try to I think I will need more to think about it, but there is no reason that it's false. But what I would be interested in is to understand why, considering the Falling set size, it gives a lower bound on the best protocol. It's something here I do not understand.
I don't either, but if you want to read the paper, it's in the paper.
The argument. Because I do not understand why.
Yeah.
But it's you can go on.
And also, so this non-deterministic bounds.
Yes.
So if I prove something for a number and a number in another case, and then for any if I multiply these two numbers for whatever alpha, and I find that the property that I'm trying to hold, I can claim that the complexity, the non-deterministic complexity is whatever. I mean, it seems
that's what they do. I was a bit confused too, but they don't explain why they do that. So
I may find another specific combination of n and m where the complexity is completely another one, but it holds for an infinitely number of combinations n and m, and I would claim this is the computational complexity. Now I have two or lower computational complexities that kind of contradict themselves.
They don't contradict themselves. It's just that you have one. A lower bound is a lower bound. So if one is less than the other, you just take the strongest one. So
But
here
it
is
talks only for some combinations of n and m that respect some properties in the first case and then in the second. So it's, but maybe people do like this.
I think it's just because, again, it's with the definition of communication complexity, which is the worst case of the best scenario. And so you see here, it's just kind of exhibiting a worst case. I think maybe we could see it like that, but again, it was a bit confusing for me too, this non-deterministic thing. So, okay. So here, just to conclude on this, here it's the proof of plurality. There is a similar proof with plurality with runoff, which consists of basically designing the same Falling set and you obtain the same bound. And so here, you just to conclude, the lower bound and the upper bound match. So, which is the case for every voting rule except this one, STV. So first, STV, it's a procedure that use successive rounds until there is a winner. So at each round, you take the votes of the people and you eliminate the candidate appearing as at the top on the fewest ballots. And then you update the profile, so you remove the weakest candidate, and then people vote again, etc., etc., until there is a winner. I will show you an example. It will be, I think, more clear. So here we have 3 candidates, and here are all the possible rankings, and here are the voters. So 417 voters voted A, B, C. Okay, so A is preferred to B is preferred to C. So first we need to count the number of people that have A as their top candidate. So we have this number of people that prefer A. We have 500 people that prefer B, and around 600 people that prefer C. So here the weakest candidate is A because it's the candidate that has the least top votes. So we remove A, and so all these people now will be associated to the ranking B is preferred to C, and all these people are associated to the ranking C is preferred to B. And so when you update, it gives this. And now B is the winner because it's the candidate that has the most votes. So just saying C is eliminated. Okay. Yes.
For me, it is a generalization of the 2 rounds in France.
Yes.
Instead of eliminating n-2 candidates, you eliminate 1 candidate each time.
Yeah. Yes.
It's very similar.
Yeah. It's not. Yeah. Okay. So now for the upper bound, again, the proof consists in designing a communication protocol. So here you can see that you can still do the general approach, right? To communicate the ranking and then someone do things and then you end up with the result, but you can actually do slightly better. So here is the procedure proposed in the paper. So for each voter, you ask them their top candidates, and then until there is a candidate A that is ranked by the majority, you just repeat the operation that I detailed previously. So you remove the candidate ranked first by the fewest voters, but now the thing you will do to reduce the number of bits communicated is that you are just going to ask the people that had the remained candidate as their top, which one is their second. So you don't ask everyone to repeat their preference, but just the people that had this person as their favorite. And this number of people, there is at most n divided by m, because if you take all candidates m, so at the first step, okay, so it depends how many candidates you have removed, but at the first step, you have m candidates, and you know that, for example, candidate C has been eliminated. So you know that C has not more than one other m% of the votes, because otherwise it would not be eliminated because it would be a better than the mean, which is not possible. And so because at every step, so at first step, you ask at most n divided by m people, then at the second step, n divided by m minus 1, etc., etc. So you ask at most n divided by m factorial people, and so it compensates with the log m factorial. And that's why here, instead of n m log m, you have n log m log m. Because at every step you ask less, you don't ask everyone, but you ask a fewer subset of the voters. Okay. Okay, so this is for the upper bound. They give a lower bound, but they don't exhibit the Fooling set. So I don't know what is the Fooling set for the lower bound, but the lower bound here does not match this upper bound. The lower bound is n log m. So STV is the only voting rule where they didn't find a bound that matched for the lower and the upper. There is another paper, not this one, but yes.
STV cannot be is more complex than plurality in terms of communication. So.
No, for the lower bound, it's the same as plurality.
Yeah.
Yeah.
Yeah. Sorry, I didn't understand what you. Sorry.
It's just that the lower bound and the upper bound do not match for STV. But just to comment on this upper bound, more late paper, so a paper that was written after this one, designed another protocol that is a bit better than this one. And they do simulations to see if actually this upper bound is like too high. And they indeed show with simulations that usually they are not at this bound. In the worst case, they are a bit less. So it seems that there is a bound better than this one that could be found. Okay.
Yes. Maybe I have an explanation for the Fooling set technique.
Mm-hmm.
Can I just?
Yes, sure.
So, what I read. Very.
Yes, I think it will be okay.
I would just explain what I understood for the case of a function with two arguments. So here we have n arguments because we have n voters. But in the general case, if you want to compute a function with n arguments, so I assume that you don't really see very well what I do, but here, for example, you have the possible argument for the first argument. Here you have the possible argument for the second argument. Here, 1, 2, 3, 4, 5. Okay. So this is just the table giving the values of my function for the first argument. X.
How this relate to voters and candidates?
Yeah, sure. Oh. So here it will be in picture just that this is the first voter. These are rankings. This is the second voters. I have only two voters. Okay. And more generally, I want to compute a function of two arguments. But one argument is Ludovic has the argument. The other argument, François has the argument. And I want to know how much information we should exchange before I am able to compute the value of the function. So that's exactly what we want to do with voting. We want to compute the winner from an information that you have and an information that François has. Okay? Okay, so now imagine, so here in this picture, you can imagine that there are some rectangles where the value is the same. Value, I don't know, A. Okay. A, here maybe it's B, here it's C, and so on. Okay, some value for the function. Okay, so I can pave my my table here with rectangles, monochromatic rectangles that have the same value. Okay.
And why rectangles?
If it's not rectangles, just you take rectangles. So here, for example, I have one rectangle here and one rectangle here. Okay. So this is exactly what you do, by the way, when you want to compress an image for some encoding. And essentially, apparently, a central theorem in communication complexity says that essentially, if you cannot pave this table with less than k monochromatic rectangles, then the communication complexity is at least log of k. This is quite intuitive when you're used to mechanisms of image compression and stuff like that. And in fact, so this is the first step. So the first step is to say, okay, I will have a lower bound on the communication complexity by paving the table of the values of my function into rectangles. And if I have more than 2 arguments, of course, it will be the generalization of rectangles in higher dimensions. Okay. And now, what is a full set? A full set. So you take vectors. So you take arguments. So for example, x equal b, y is equal to 3, for example, and so this is one element of the Fooling set. Another element will be x equals c and y equal to blah blah blah. Okay, and essentially what it says is that in that Fooling set, you will have the same value here for example b3 and c4. Let's say you have the same value here. Let's say v. But as soon as you change the value, you change the value of the function. So since it's a Fooling set, you know that here, if you keep this value for y, but you take the value of the other for x here, you will have something else. And here you will have something else. So this proves that in fact you have many monochromatic rectangles. You see? And in fact, you can show that if you have a Fooling set of size k, then you will have at least k monochromatic rectangles, and hence a communication complexity of at least log of k.
Leading to compression.
Yeah.
Okay. Thanks.
So the order of the columns is important. So this k can change if you switch the b with c. This is why.
Maybe no. I think that a rectangle is to be taken in a more general sense.
Okay.
So, for example, I think that this union this is also a rectangle. I think.
Okay.
I've not read much on the subject, but.
Okay, how many time? Okay, so maybe for the end of the talk, I'm not gonna tell much about. Maybe I will just explain you the voting rules I was planning to talk about, and then show you the general table. So maybe you can like look it if you if you can like agree intuitively with the bounds. Like, okay, this voting rule actually needs more information, and because I don't think I will have the time to detail everything. So the next one was the Condorcet rule. So the Condorcet rule elects the Condorcet winner whenever there exists one. I have 2 examples of one profile that have a Condorcet winner and one that doesn't. So the Condorcet winner is just a candidate that wins all their pairwise comparisons. So here, for example, if you look at the watermelon, it wins against the orange here, here, and here. So you have 3 votes that prefer the watermelon to the orange. And it also wins against the banana 3 times, here, here, and here. So you have a majority of votes that prefer the watermelon to the orange, and the majority of votes that also prefer, that prefer the watermelon to the banana. So here, the watermelon is a Condorcet winner. And here you have a cycle. You don't have any Condorcet winner. And so what's important here is actually not the ranking, but the pairwise comparison. And this will show actually in the communication complexity, because just to say a few words about it, you will just need to look at the comparison between two candidates. And so the central authority will give the pairwise comparison to the voter, and the voter just need to say which one they prefer. So it's just one bit, because you just give one for, the pair. So you have a pair that is numbered, and you just give your favorite. And so this is why you can do better again than the general bound, because you just look at the pairwise comparisons. Yes.
Think about another question that I didn't have at the beginning. You can't, in terms of communication, you can't only the communication from voters to the central DT.
No.
Or also the other.
Also the other way around, but usually the other way around you can ignore it because it's less than the first one.
Here it's not the case.
Yes, here it's not the case. Yeah.
So you consider election systems where there may be the empty set as the reason.
Yes, that's another comment. In fact, yes, here they assume that sometimes the Condorcet rule does not elect any winner, and they don't take into account the breaking ties, because it's an operation you do out of the communication thing, and so it doesn't count.
The empty set and
yes.
But it does, to produce the empty set as a cost.
Yes, it's a possibility.
And you analyze this cost.
But even if you had to break ties, it would not really impact the communication.
The ties, but so if there is no Condorcet winner, you return the empty set, but
yes.
it costs something to be that.
Yes.
And this is the cost you.
It may be the oldest candidate who win in that case.
Yeah.
For example. This is
yes. Okay, so this is just what I explained, but with the detail. And so this produced an upper bound of big O of NM, because that's what I told you before. You don't have log M when you exhibit your preference among a pairwise comparison, because just one bit saying I prefer 1 or I prefer 2. And there's also a lower bound that is of omega and M. Again, yes.
Can you show the previous line?
Yeah. So in substance, this protocol, you just at the beginning have every candidate. You have a list of candidates. You take the first 2 and you ask people, which one do you prefer among those 2? And basically you remove the one that is less preferred, and you do this until you have 1 candidate. You just check that the last candidate is a Condorcet winner or not, and that's it. So but I just don't want to detail a lot about this because I don't have much time.
Yeah. I was just intrigued by the if S is empty, no Condorcet winner exists, but that can happen just in case of tie in the pairwise comparison.
Yes. So here you have 2 conditions where you don't have a Condorcet winner, and one corresponds to ties and the other corresponds to.
So it's same because you don't ask the user to keep 2 voters all the pairs, but just the pairs that remain.
Yes, exactly. Okay, so you also have a lower bound. Again, it consists of designing a Fooling set. I will not explain the Fooling set, but just to you made the remark earlier, if the Fooling set was a ranking or just like a vector of rankings or a vector of like only candidates. Here you need the ranking, so the Fooling set exhibits it's a vector of rankings, contrary to plurality where it was just your favorite candidate because you only needed this information. Okay, so approval voting, I will just comment quickly. It's a voting system where you can approve several candidates instead of just one. So it's a generalization of plurality. And this is the only voting system that is not ranked based. And that's it. That's what I'm going to say. I will show you the table at the end. And Borda counts. Maybe I will not detail this one. So for Borda count, you just have a ranking, and the first one gets M-1 point, the second M-2, etc. until the last one that gets 0, and the winner is the candidate that has the most points. And just to comment on this, because you have to give the full ranking in order to get all the points, this implies that the communication complexity of this one is bigger than the other one, because you cannot find a system where you get rid of this, the fact that you need to give the ranking. And so here, for the summary table, you see that Borda, you cannot, like the lower bound is nm log m, because you have to provide the full ranking. You don't have, like, for example, in Condorcet, you do not necessarily need to give the whole ranking, but for this one, yes. So just to comment on this, as you can see, the plurality and the STV, they are the best in terms of communication complexity. Then you have Condorcet, which is a bit after them. Approval has the same complexity as Condorcet. It's not necessarily intuitive to me, but I trust the paper. And then you have Borda, Copeland, and rank pairs. If you want to discuss any of the voting system I haven't talked about, we can talk about it later during the break. And if you have any questions, don't hesitate. Yes.
Perhaps not a question, but more something that perhaps was done. So I think in terms of communication, right? So if you add the number of bits that you transmit, this would be the case on coax, and all the users are on the central entity are on this coax, and this would be the time, even to communicate, sort of, right? Something like that, or to get the result. Assume I want to do, I don't know whether it exists by analogy, there is fast trading, there could be also fast voting, right? You want to get the result as fast as possible. And assume now you change the assumption of the coax by a star network or a shared medium with a wireless medium. Then you would have a complexity in time, which is not captured by this analysis of number of bits, but that would depend on the structure of the network. And my question is whether this was considered, I mean, to look at, so if you had a star network with the central entity, you would not have the n, right?
Yes.
If you would have a shared wireless medium, then you would have this multiple access scheme type of coding questions that we were discussing earlier that came to my mind early after at the beginning of your talk. And so, I mean, are there instances of this complexity things where you would take time and the structure of the network as objective rather than number of bits? So
that's a good question. I don't know. I don't think it has been done, but I cannot like ensure it.
Then you could think of wireless voting, right? Or I mean, I mean, entangle the topology of the network.
Yeah.
If you distribute, you could have a mesh. You could distribute your voters and the central entity, and there would be a complexity in time.
To my knowledge, it hasn't been done, but again, I'm not sure.
Because you can ignore that because Condorcet, no? Yeah, it seems complexity is not so bad. But then if you implement this, for instance, to vote real president, you should have a lot of go up and forth, you know, asking users. Okay, so it would take like centuries to do one election. But from the complexity, you don't know. So time and complexity are very, very different.
But I think that's one of the critiques we can make, that some of the protocols that has been provided are not necessarily like able to be done in practice, because you could not ask people to give you their opinion like that many times, and provide a ranking in a sense would be more practical than like doing this protocol
there are enough studies like examining this, what you can parallelize or what should be sequential?
No, I think most of the work that has been done with this is like purely theoretical, and but I think when they talk about this, they like say that one of the critics is that it's not really like in the purpose of being applied in practice, but just to look at the thing theoretically, like what would be the communication for that.
Theoretical.
But is fast voting any, I mean, fast trading is absolutely fantastically important, right? I mean, in terms of, but is fast voting of any importance?
What? I don't know. Yeah.
I think in you know, self-organized systems or whatever, I think it's important.
In distributed systems,
Yeah,
to elect
someone.
This made me think about the consensus problem, the Byzantine agreement. Algorithms. So let's say take into account the number of rounds, so it's time.
Time is okay.
And that is why I was thinking on other things. So we know that with classical Byzantine agreement, we have a number of steps that increase with n. I don't know exactly if it's square root of n or n log n, and maybe n divided by log n, something like that. But in quantum, it is constant. If you use the quantum version of the Byzantine agreement.
Yeah, I think typically there are two fields that don't talk that much to each other. The first one being voting, where people are more concerned by complicated voting rules, Condorcet, blah, 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 and so on. And distributed computing, where typically people take into account the topology of the network and stuff like that, but typically use plurality. In fact, just want to see what is the majority, what option has the most votes or something like that. But so maybe there is an intersection here that is not covered by any of the two fields.
Again, Stevie is not so bad.
But for fast trading, you know that fast trading led to financing more mathematics in the US than NSF, because of Gene Simons, who was a mathematician, and the Renaissance technology, it became like a fortune, the order of tens of billions of dollars, and so he started funding mathematics based on the income of fast trading. So perhaps fast
voting
can start.
Another application is machine learning. No, if you have ensemble learning, and then there are different models doing prediction, you have to elect the winner. These voting systems can be relevant. I don't know if you heard about anything about that. You know, ensemble learning.
So it's a bit true, but so typically what you have in ensemble learning is that you have options with values. So each model gives a value to each option, and then you need to gather the results and something like that. Whereas most of the time, voting theory is based on rankings. And it's very different because many of the issues that you have in usual voting theory come from the fact that you do not have a numerical evaluation of the options.
Yeah, but there are now a new round of papers about learning how to rank. So where the model has to learn how people have preferences among objects. So the numerical values is not interesting.
Yeah.
And they try to get rid of the numerical values. They want to go to the ranking. So that's those things can be or preference elicitation or stuff like that.
Okay, so if no more questions, I think we can go have lunch. Oh, okay, you have.
And for STV, I mean, so this not matching of operand lower bound means what? It's just a lack of understanding, or is it something more?
It seems that is a lack of understanding because a paper that has been written after this one shows that first they give a better protocol for the lower bound, no, sorry, for the upper bound. And then they show with simulations that actually this upper bound is never like reached. That is, the complexity is lower. So it seems that maybe there could be an improvement here.
So possibly the right answer would be n log n.
Yes.
If, yes. Yeah, and so, but at one day, one perhaps interesting question would be to try to understand the theorem and the rationale that seems
sure.
to be linked to source code, right? To compression. Right? So that would be very interesting for us for me to understand that. So perhaps it's some request.
In fact, I have no access to my Nokia email for the moment, so I just sent an email to Christina so that she can send it to everybody.
It is on the chat.
It's on the chat. Thank you. Thank you very much.
With the paper.
With a course explaining the theorem, with the full insets and blah blah blah.
Okay.
That's very good. Okay. Beautiful lecture. Thank you.
Thank you.
Alors, j'imagine que si tu nous as présenté ça, c'est que Jérôme a
Oui.
des idées pour travailler sur
Ouais,
ce truc.
Bah justement sur le truc STV, de voir si on peut pas obtenir mieux.
Merci STV.